Welcome to solverfy.
Okay, so assuming the switch is open, we have this following setup here. Now, we're looking for the EMF of the battery, which we'll denote with the epsilon there. And so we're going to use Kirchhoff's second law for this. Now, this is his loop rule. And what this means is that when we draw a loop, any loop in the circuit, the sum of all the differences in potential around that loop will be 0. So this circuit contains two loops, one on the right-hand side and one on the left-hand side. So let's draw some loops with some directions on there. I'm drawing these in red. There we go. And specifically, Kirchhoff's law says that around that loop, well, let's go back to black. All right, around that loop, the difference in potential around the loop has to equal 0. Now, change of potentials include the potential drops due to everything in this circuit. So this includes the battery as well as all the resistors. So let's specifically talk about the right-hand side loop. Okay, so the battery here is going to raise the potential, and then it's going to drop across all the resistors. So the signs on the resistors are going to be opposite that of the battery, and that's how they're going to equal 0. And we can actually write that out equation-wise. And so we have, let's get a new sheet up here. So expanding this out, we have the EMF minus the potential difference across the 20 ohm resistor minus the potential drop across the 30 ohm resistor minus potential drop again across the 50 ohm resistor is equal to 0. Great. So now, basically, if we can find all these drops in potential, these three, we'll find the EMF of the battery. So we're already given this in the problem, the change in potential across the 50 ohm resistor. That was 15 volts, right? So now we need to find the change potential across the 30 ohm resistor, and we do that using Ohm's law. So I'm not going to review Ohm's law because that was done in previous chapters, but we can find the current in this in the 50 ohm resistor using Ohm's law, and that current is the same as in the 30 ohm resistor because these two are in series, and that current is going to be 0.3 amps, and you can get that just by dividing 15 by 50. So that's 0.3 amps. Excellent. Okay, we can also use Ohm's law with this current 3 amps and this 30 ohm resistor to find the voltage drop across that 30 ohm resistor. Again, I'm not going to get into that just because we already did that in previous chapters. It's 9 volts. Great. So now we see that if we add together this 15 volt drop across the 50 ohm resistor and the 9 volt drop across the 30 ohm resistor, we're going to get 24 volts across this half of the circuit. Now, these two resistors are actually in parallel with this other 75 ohm resistor. And that means that the voltage drop across the 75 ohm resistor is actually equal to the voltage drop across the other two. And that's actually going to become really relevant for us in a second. So let's just rewrite what we've got here. Let's say, okay, the EMF is equal to, then we're going to move all these voltages onto the other side and make them positive. So this is the change in voltage across the 20 ohm resistor, and then plus that other 24 volts that we had. Remember, the 24 volts is just the 9 plus the 16, or plus the 15. Great. So now we have that. So now we just have to find this voltage drop across the 20 ohm resistor. And we're going to do that again with Ohm's law. So delta V is equal to IR. Great. But we need to know the current. So let's go back to our picture here. And we know the current in the right half. And we know we can find the current in the left half. And then because of Kirchhoff's first law, because of Kirchhoff's first law, those two currents are going to combine at this juncture, and they're both going to pass through this 20 ohm resistor. So we can use Ohm's law to find the current through this 75 ohm resistor. I'm not going to go into that, but it is, let's see, where did I write this? 0.32 amps. So the I here is 0.32 amps. And that's just dividing 24 volts by 75 ohms. So anyway, we can say, okay, this 0.32 amps, that's what's going around here. And then we have this 0.3 amps going around there. They're going to combine here, and we have 0.62 amps coming down the 20 ohm resistor. So they're going to combine and to make this current going through the 20 ohm resistor. And then we get some more Ohm's law, and we can again find that that current, or that change of potential through Ohm's law, and that gives us, ultimately, we have 0.62 amps, and we're going to multiply that by 20 ohms, and then add on our 24 volts from the other side. And at the end of this, the EMF of our battery is going to be 36.4 volts. Excellent. Okay, now part B is another example of Kirchhoff's second law, but it's actually a lot simpler of a problem. We just have a 25 volt battery and a 50 ohm resistor. And we basically say, since we only have one loop here, this is 25 volts, 50 ohms. Since we only have one loop, let's just draw the loop. The total voltage drop we get across all these things is 0. And that means that this potential, or this change in potential, has to be equal to this change in potential. And that means we can just apply Ohm's law. So basically means that the voltage of the battery is equal to the current that goes through the loop times the resistance of that resistor. So basically, this tells us then that the current going through there is voltage over resistance. So it comes out to be 0.5 amps. There you go.